Hello everyone and welcome back to another calculus video. In this video we are going to discuss limits at infinity and asymptotes, and more specifically we're going to talk about horizontal asymptotes. And horizontal asymptotes will help us describe the end behavior of different types of functions, such as rational functions. And we're going to be able to understand why the rules for rational functions and the end behavior test for polynomials worked from our pre-cal algebra class. So let's get started. When we're talking about taking a limit at infinity, we're talking about what happens as x gets super big or as x gets super small. And if this limit approaches a specific value, L, then we say that limit is going to exist, and it's going to exist at this specific spot, which means that we're going to have a horizontal asymptote for that type of function. So let's look at a few examples. For each of these, we want to look at what happens as x gets super big, so as x goes to infinity, and as x gets super small, so as x goes to negative infinity. And that's going to help us find the horizontal asymptotes. That's actually how you find a horizontal asymptote. You take the limit as x gets big and as x gets small. So if we were to look at this guy, we're going to take the limit as x goes to infinity, and then we're going to take the limit again as x goes to negative infinity. So we're going to have 5 minus 2 over x squared. So we're going to use some limit properties here. We know that the limit of the difference is the difference of the limit. So I could rewrite this way. And I'm going to think about what happens as x gets really large. Now, this guy is the limit of a constant, so we know that's going to 5. The question is what's happening here. So we're going to think about plugging in really large values. Like what happens if I plug in 1,000,000? Well, if I plug in 1,000,000 and I square it, I'm going to have a super big denominator, and 2 divided by a really big denominator is going to head to 0. So this whole limit is heading to the value of 0, which means the limit of that expression is going to 5, which means that this guy has a horizontal asymptote at y equals 5. Remember, horizontal asymptotes are in the form of y equals something. Now let's look at what happens as x approaches negative infinity. So we're going to have 5 minus 2 over x squared again. I'm still going to think about it the same way by splitting this up using my limit properties from that first chapter when we first started talking about calculus stuff. Again, this guy is going to 5. The question is what's happening to this guy. So as I plug in really small values, like negative 1,000,000, negative 1,000,000,000, that denominator is still getting large. It's going to be a positive denominator because I'm squaring all of those negative numbers. But even if it wasn't a positive, that denominator is getting small, that big, so that 2 over that large denominator is still heading to 0. So this guy has a horizontal asymptote at y equals 0. So let's take a minute and look at the graph. So I've graphed y equals 5 minus 2 over x squared. So you can see that graph. So you can see as x gets really large over here, all those y values are heading towards 5. On the left-hand side, all the y values are heading towards 5 also as x gets super small. Even if I were to zoom out quite a bit, you're going to see the same thing. We could follow that graph. We're never going to quite reach 5, but we're going to get super close to it as x gets really big or really small. And that's all that limit at infinity is telling you. So let's look at that next one. We want to know what happens as we approach infinity and negative infinity for sine of x over x. So this is part B. We're going to take the limit as x approaches infinity and negative infinity of sine of x over x. So let's think about what's happening with these. If I take the limit as x goes into infinity of a quotient, I could think about taking the limit of the numerator and the denominator separately. And then I could think about what's happening with each of those pieces. So if I look at what happens with sine, as I plug numbers into the sine function, and I'm plugging in numbers that are heading towards infinity, so super big numbers, the sine function, if you remember back to trig class, looks like this, right? Just kind of oscillates. And it's going to always oscillate between a positive 1 and a negative 1. So the biggest this thing can be is positive 1, and the smallest it can be is negative 1. So that sine function is bounded between those two values. So I'm going to go with the larger value because it doesn't really matter how we look at this point. That denominator, as x gets larger and larger, is heading towards infinity. So this guy is getting super big. So instead of saying equals, let me say approaches. So if this is limited at most to being a 1, and these values down in the denominator are getting bigger and bigger and bigger, then that whole fraction is shrinking towards 0, and that's on that right-hand side of the graph. Likewise, we could look at this the same way. As x goes to negative infinity, that sine is still bounded between between negative 1 and 1, and that x value is getting smaller and smaller and smaller. So at most, this could be a positive 1. The smallest it could be would be a negative 1. That denominator is decreasing without bound. And if I take 1 and divide it by a super small number, like 1 million or 1 billion, I'm still heading towards 0. If we look at that graph, here's sine of x over x. You can see what this graph looks like. And if we were to zoom out, as x gets smaller and larger and larger, we're heading towards y equals 0 on the left, on the right, and on the left. As x gets smaller and smaller, we're heading towards y equals 0. So we would say that horizontal asymptote is going to be y equals 0. And then let's look at that last one. Draw a line here, and we will look at C. We're going to take the limit as x approaches infinity of the arctan, and then the limit as x approaches negative infinity of the arctan. So I'm going to start this one by graphing it. So we're going to go x. So you can see as x gets larger and larger over here, we're heading towards pi over 2. And as x is getting smaller and smaller, we're heading towards negative pi over 2. So this guy is going to have two horizontal asymptotes, one at pi over 2 and one at negative pi over 2. This guy on the right is heading to pi over 2. On the left is heading to negative pi over 2. So let's think about this in terms of its inverse function, the tangent function. So we know tangent of x has vertical asymptotes. Tangent's really sine over cosine. So anywhere that cosine would be 0 would give us a vertical asymptote. which means we would have vertical asymptotes at pi over 2 and at negative pi over 2. If we were to graph this function, the tangent function, we would see the function would be undefined at pi over 2 and negative pi over 2. That goes back to the unit circle. So our unit circle looks like this. This is where the x-coordinate would be 0. That's happening at pi over 2, and that's also happening at negative pi over 2. And we're going to have a lot of them. 3 pi over 2, 5 pi over 2. It's odd integer multiples of pi over 2, either going around the circle this way or around the other way. So remember to find the inverse function though, because that tangent function looks something like this, right? And there's a whole bunch of different iterations of this. We had to make it 1-to-1, which means we defined tangent to be between negative pi over 2 and pi over 2. So we didn't worry about what happened to the right of pi over 2 or to the left of negative pi over 2. To find an inverse, it has to be a 1-to-1. So if we define this to be on negative pi over 2 to pi over 2, then we can find the inverse, which is the arctan, or the inverse tan. If I have a vertical asymptote for the tangent function, then the inverse tangent function would have horizontal asymptotes at those same places. So you can see how we're starting to tie in this idea of inverse functions and everything you learned from pre-cal algebra with your trig stuff from pre-cal trig. Okay, let's look at another one. Let's say you want to find horizontal asymptotes for this function. Y equals 3 plus 4 over x. To do that, we're going to take the limit as x approaches negative 3 from the left and negative 3 from the right. And this is where, negative infinity as x approaches negative infinity and as x approaches positive infinity. So this is where you may want to pause the video, try it, come back, and check your answer. So if I take the limit as x approaches negative infinity of 3 plus 4 over x, we could think about using limit properties. Take the limit as x approaches negative infinity of 3 plus the limit as x approaches negative infinity of 4 over x. This guy is going to go to 3. This guy, as x gets smaller and smaller, that fraction is also getting smaller and smaller. So this is approaching 3. Likewise, as x approaches infinity of 3 plus 4 over x, we could think about the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 4 over x. This guy is going to 3, whereas this guy, as x gets larger and larger, that fraction is shrinking, so it's approaching 0, and we're going to get 3. So we can say that a function has an infinite limit if, when we think about what happens as x gets larger and larger, or as x gets smaller and smaller, because we could think about this in terms of negative infinity too, if we approach infinity. And this happens a lot with polynomials. So I'm not worried about using that formal definition here. What I want to do is I want to change the problem. Instead of doing this, let's look at what happens as we look at a polynomial. Maybe we look at 3x to the 5th. We want to know what's going to happen to that limit. So you may remember the end behavior test from 171. So the end behavior test looked at if you had an even or an odd as your biggest exponent, and then if the leading coefficient was positive or the leading coefficient was negative. We said if we had an even leading term and a positive leading coefficient, both ends would point up. So we could think about the limit as x goes to infinity heading up and the limit as x goes to negative infinity heading up, both sides to positive infinity. If we had a negative leading coefficient but an even for that leading term's exponent, then both ends would point down. If we had an odd leading coefficient, the left-hand side would point down, the right-hand side would point up. Whereas if we had a negative leading coefficient, the left-hand side would point up, the right-hand side would point down. So if we were to look at this one, we have 3x to the fifth. This has a positive leading coefficient and an odd exponent, so we would expect it to look like this on the ends. So let's do this using calculus now. If we plug in super big numbers in here, so I'm thinking a million or a billion, we're going to have 3 times a million raised to the fifth power. Well, this is just going to get larger and larger and larger as our x value gets bigger and bigger and bigger, which is why that side's heading to infinity, which is the same thing that the end behavior test would tell us. Let's look at what happens as x approaches negative infinity. So as x gets smaller and smaller and smaller, we're plugging in values like negative 1 billion, negative 1 trillion. If I take a negative number and I raise it to an odd exponent, it's going to be an odd number. So I have an odd number times I have a negative number times a positive number. So a negative times a positive is going to give us a negative, which means this is heading towards negative infinity. That's exactly what our end behavior test would tell us. So let's look at the graph for this one. We're looking at y equals 3x to the fifth. Does our graph agree? Maybe try to resize this. So as x is getting larger and larger, you see those y values are heading up towards infinity. Whereas if x is getting smaller and smaller, all those y values are heading to negative infinity. So what's interesting about this, it really depends on that leading term. Even if we would have had stuff after this, like a 4x cubed plus x squared, what would happen is when I take that limit, let me see if I can scoot some of this over. Here's the way we would look at this. If I were to take that limit as x approaches infinity of that, as x gets larger and larger, this term is going to outweigh these terms. So I don't even have to really think about what's going on with those. I really just care about what's going on with that leading term. The leading term is going to be the x with the biggest exponent. So that's why this rule works so well, because as x gets larger, all of your other terms really become insignificant. When I think about raising a billion to the fifth power, it's going to outweigh what happens with that cubed and that squared. Same thing over here. If I were looking at what happens as x goes to negative infinity of that 3x to the fifth plus 4x cubed plus x squared, it's going to approach what happens with that limit of that leading term, which is going to result in this little consequence. It's going to head to negative infinity as x gets smaller and smaller. Let's show that on the graph. I've already forgotten what I wrote. 4x cubed plus x squared. And you can see our graph agrees with us. As x gets larger and larger, those y values are getting larger and larger. And as x gets smaller and smaller, those y values are getting smaller and smaller. So this is where you may want to pause the video, try these, and then come back and check your answers. So if we were to look at this first one, we're going to take the limit as x approaches infinity and the limit as x approaches negative infinity. We're doing this for negative 5x cubed. So as x approaches positive infinity, we're plugging in really large values and we are raising them to the third power. So I'm going to have a positive here, and a positive times a negative would give me a negative, which means this is heading to negative infinity. Here, if I plug in negatives and I raise it to the third power, I'm going to end up getting a negative, and a negative times a negative will give us a positive. So that's what we would expect to happen. We were thinking about this on that graph, that Cartesian plane. On that right-hand side, it's going to head to negative infinity. On the right-hand side, it's going to head to negative infinity. On that left-hand side, it's going to head to positive infinity, which agrees with our end behavior test, because this would be an odd exponent with a negative leading coefficient. If we were to graph it, we're going to have that same result coming out. You zoom in so we can see this. Going to head up to negative infinity as x gets smaller. Positive infinity as x gets smaller, negative infinity as x gets larger. B, taking the limit as x approaches infinity of 2x to the fourth, and as x approaches negative infinity. So as x gets larger and larger, this is going to be a positive because I'm raising it to the fourth power, and a positive times a positive is going to be a positive. Same kind of thing here. Negatives raised to an even power will end up being positive, and positive times a positive is a positive. So we would expect both sides to go up. There could be some twists and turns like we know from pre-cal in the middle. I'm not worried about what happens in the middle. I want end behavior only. Going back to end behavior test, even leading term with a positive exponent means both sides are going to be heading up, and you can confirm that by graphing it. This was 2x to the fourth. Both sides are going up. The end behavior test also works for rational functions, so let's review those rules from pre-cal. We said we had a set of rules for horizontal asymptote. We said we look at the degree of the numerator and the denominator. So if the degree of the numerator is equal to the degree of the denominator, horizontal asymptote was the ratio of the leading coefficients. So for this guy, what would happen is we would say the horizontal asymptote would be y equals 3 over 2 because of the degree of the top and bottom are both 1. So that was rule 1. Rule 2 said if the degree of the numerator was less than the degree of the denominator, the horizontal asymptote was y equals 0. So if I look at part B, I would expect it to be y equals 0. And then 3 says if the degree of the top outweighed the degree of the bottom, there are no horizontal asymptotes. You could have an oblique asymptote if the degree of the top is one more than the degree of the denominator. So those are the rules that we had. Now let's look at the calculus reason why that works. That's what we're going to talk about in this problem. So I'm going to go back to A. I would take the limit as x approaches infinity of 3x minus 1 over 2x plus 5. So let's think about what's going to happen here. So here's the trick we're going to use. We are going to divide the top and bottom by the largest power of x in the denominator. So the largest power x in the denominator is x. So here's what I'm going to do. I'm going to think about it this way. I am going to divide everything by x, top and bottom. As long as I do the same thing to the top and bottom of the fraction, it is a legal move in math. And then I'm going to split that numerator. That's something we've seen quite a bit here. So I'm going to have 3x over x, which is just 3, minus 1 over x, over. Now I have 2x over x, which is just 2, plus 5 over x. And that makes it easy for us to think about the limit. And we're going to use those processes that we talked about earlier. The limit of the quotient is the quotient of the limit. So I can take the limit of the top and the bottom separately. As x gets larger and larger, that top is going to 3 minus 0. That bottom is going to 2 plus 5. Remember, as x gets bigger, this and this are getting smaller. So this is, sorry, not 5. 2 plus 0. As x gets larger, that fraction is shrinking to 0. So this is approaching 3 over 2. So what's interesting is that I could think about this going to positive infinity or negative infinity, and I'm going to get the same result. That only happens when we have a rational function, which means a polynomial divided by a polynomial. So as I approach negative infinity, this guy is still going to go to 0. Same thing with this. So that top is still going to go to 3, and that bottom is still going to go to 2. Let's look at part B. We're going to do the same thing. We're going to take that limit as x approaches infinity, or we could think about negative infinity. Your textbook's going to use a plus and minus there. So we have 3x squared plus 2x over 4x cubed minus 5x plus 7. So we're going to divide the top and bottom by the biggest x with the exponent in the bottom. The biggest thing I see in the bottom is that x cubed. So let's divide everything by x cubed. So I have 3x squared plus 2x all over x cubed. And then I have 4x cubed minus 5x plus 7 all over x cubed. So I'm going to have 3x squared over x cubed, which is 3 over x. 2x over x cubed is 2 over x squared. 4x cubed over x cubed is 4. 5x over x cubed is 5 over x squared. And then we're going to have 7 over x cubed. So let's think about what's happening here. So as x gets larger and larger, this is going to 0, this is going to 0, this is going to 4, and then these two are going to 0. So I've got this heading to 0 over 4, which is heading to 0. So that's why that horizontal asymptote is going to be 0. And then let's look at part C. just a second to fix this. That's an x cubed. All right, part C. We're going to take the limit as x goes to infinity, 3x squared plus 4x over x plus 2. Just like before, we're going to divide the top and bottom by the largest x with the exponent in the bottom. Now, the biggest thing I have in the bottom is an x. That's really different from the ones before. So we have 3x squared plus 4x all over x, and that's divided by x plus 2 all over x. So let's simplify this. So I'm going to have 3x squared over x, which is 3x, plus 4x over x, which is 4. X over x is 1. 2 over x is 2 over x. So as we head to infinity, this guy is going to get really big. So adding 4 to it's not going to make a big difference at all. This is going to head to 0. So I'm going to have infinity over 1, which is going to head to infinity. So as x gets larger and larger, this is going to head to infinity. But remember, the degree of the top is bigger than the degree of the bottom. We do not have a horizontal asymptote, but we can still tell what's happening on the right and on the left. This is part C. Continued. Now let's take the limit as x approaches negative infinity. So I'm still going to divide everything by x in the top and bottom, which would still give me this. So I'm going to start there. 3x plus 4 over 1 plus 2 over x. So as x gets smaller and smaller, this is going to head to negative infinity. And adding 4 to negative infinity is really not going to make a difference. But this guy is still going to head to 0. So this is going to be negative infinity over 1, which is going to be negative infinity. So there's both my pieces. My oblique asymptote would be right here. So as x goes to positive infinity, you can see how those y values are going to get larger. As x goes to negative infinity, you can see how those y values would get smaller. Let's look at another one. We want to find the limits as x approaches infinity and negative infinity for 3x minus 2 over the square root squared plus 5. So we're going to use that same trick where we are going to divide the top and the bottom of the fraction by the largest x in my denominator. So I have an x squared, but it's under a radical. Now, when I take the square root of x squared, I'm going to end up with the absolute value of x. And the absolute value of x is really going to be an x if x is positive, or it's going to be a negative x if x is negative. So on this, I'm going to divide the top and bottom by positive x. And I'm going to think about that positive x this way. Whereas with this, I have to think about it differently. I'm heading towards negative infinity. So I'm looking at negative x values, which means I got to divide by negative. I can choose to put that negative in the top or the bottom. And I'm going to choose to put that negative in the top. So what I'm really doing here is I'm multiplying by a negative 1 over x over 1 over x, which would give me a negative, which is going to give me that negative because this is negative infinity. This trick is always going to work. So let's simplify. I'm going to start with that top one. We draw a line here that separates all this. So I'm going to simplify this. This is not a rational function because of that square root. So we do not have a nice set of rules. This is the only way to find the horizontal asymptote. 3x over x is a 3. When I think about this, I'm using square root properties. So I could think about that as 4x squared plus 5 all over x squared, instead of taking the square root of the top and the bottom separately. And this is going to simplify to a 4 plus 5 over x squared. So you can see why I kept it this way, even though square root of x squared as x goes to infinity would still just be an x. I am dividing the top and bottom by the same thing. So let's look at what happens as x gets large. That 2 over x is going to go to 0. This is going to be 4 plus 0, and that's under the radical. So we're going to have 3 over square root of 4, which is going to approach 3 over 2. If we head to negative infinity, so coming down here, the limit as x approaches negative infinity. So I have 3x over negative x, which is a negative 3. Negative 2 over negative x is a positive 2 over x. And I'm going to simplify this. So square root of 4 plus 5 over x squared. So this is going to head to negative 3. This is going to head to the square root of 4, which is negative 3 over 2. So this guy has two horizontal asymptotes. One at y equals 3 halves and one at y equals negative 3 halves. And if we were to graph that function, we would end up seeing that. This one's going to work the same way. I'm going to split this up, limit as x approaches positive infinity, and then the limit as x approaches negative infinity. So dividing by the largest x in the denominator, that x in the denominator is just x. So I can think about x being the square root of x squared. The question is, do I use the plus or the minus? If we're approaching positive infinity, we're going to use the plus. So we're going to take that 3x squared plus 4. We're going to divide it by x, which I'm going to write as the square root of x. And I'm going to divide that bottom by x. So I'm going to use square root properties here. So I have a 3x squared over x squared, which is 3. This is going to be a 4 over x squared. Here, this is going to be a 1 plus 6 over x. So as x gets larger and larger, this guy's going to 0. So I'm going to have 3 plus 0 under that radical on the top. I'm going to have a 1 plus 0 down here. So this is going to approach square root of 3 over 1, which is square root of 3. As I approach negative infinity, let me clean that up. Same concept, still using that same idea, except I'm going to divide by a negative x. And I'm going to put that negative in the bottom. I like to put it in the place without the square root. Oops. You write proper notation, so I'm going to scoot this guy down. This is equal to the limit as x approaches negative infinity. So now let's write that limit again and simplify the x squared. So I'm going to have 3x squared over x squared, which is 3. This is going to be a 4 over x squared. This is going to be a negative 1 plus negative 6 over x. So as x gets super small, that fraction is going to go to 0. And this fraction is going to go to 0. So this is heading towards a negative square root of 3. So again, two horizontal asymptotes. One at square root of 3, one at negative square root of 3. So let's look at one more. Let's say we want to find the limit as x approaches infinity and negative infinity of this function. We've got e to the x's in it. There's not a set of rules that's going to work for this. So we're going to have to take that limit using the same technique we did for the last two examples with the square roots. We have 3e to the x minus 4 over 5e to the x plus 2. There's our function. So here's our setup for this. So I'm going to think about it the same way. The biggest e to the x I have is in the bottom. They both are really just e to the x. But if this were an e to the 2x in the bottom, I would divide both by e to the 2x. Since I just have an e to the x, I'm going to divide the top by e to the x, and then I'm going to divide the bottom by e to the x. What I'm really doing is I'm really just multiplying the top and bottom by 1 over e to the x. As long as I do the same thing to the top and bottom, it's a legal move in math. So let's simplify. 3e to the x over e to the x is 3. This is going to be a minus 4 over e to the x. This is going to give us a 5 plus 2 over e to the x. So as x gets really large, this guy's increasing really quickly. So that whole piece, 4 over e to the x, is going to 0. Same concept down here. This is going to be a 5 plus 0. So I'm going to have a 3 over 5 for that horizontal asymptote. So think about what's happening here. So let's think about what this means. If I were to plug in really small numbers like negative 1 million, negative 1 billion, this exponent is going to be negative, right? So I'm going to have 3e, let's just plug in negative 1,000. And if I have a negative exponent, isn't that the same thing as moving that term to the denominator? So think about this guy, we're smaller, negative 1 million, negative 1 billion. Then that denominator is going to get larger and larger, so that piece is going to 0. So this is going to 0 minus 4 over 0 plus 2, which is heading to negative 4 over 2, which is a negative 2. So we have two horizontal asymptotes. We have one at 3 over 5th, or 3 over 5, and we have another one at negative 2. As x goes to negative infinity, on that left-hand side, we're approaching y equals negative 2. As x goes to infinity, we are approaching y equals 3 over 5. So that one, we didn't have to do anything fancy. We had just to think about what that means when we have negative exponents. So I tend to write things this way, thinking about negative exponents, knowing that infinity is not a number, it's a place. But that place still gets us the same idea. And it's okay to use this kind of notation. I don't know if I can get that right. There we go. Still gives us the same idea.